Hello everyone, welcome to our topic on synchronous sequential circuit analysis. This is our main lecture, lecture 2. We are looking at synchronous circuits. These are clocked circuits. The clock pulses are used as one of the inputs of the flip-flops. We seldomly show instability problems. Their timing is easily broken down into independent discrete steps. When the clock pulse is not active, the feedback loop is actually broken and the flip-flop outputs cannot change. So that is our combination circuit. Flip-flop to give us memory and the clock pulses are fed into the flip-flops. So welcome to them. The behavior of a sequential circuit, as we saw, is determined by inputs, outputs, and states of the flip-flops. And you can describe it by a state diagram or a state table. These two are the same. Both the outputs and the next state are functions of the inputs and present state, depending on whether it's milli or more. So when we say analysis, what are we really doing? We've talked about this. You start with the given circuit diagram. Then you derive a state table or a state diagram. You can be asked for the timing diagram, and if possible, you identify what it is. So that is this circuit diagram. Okay, then you look at your flip-flop equations, output, state, and transition equations, and then you come and you can give somebody a verbal description of state table and state diagram. So what are the steps? Step 1, you identify and label inputs, outputs, and internal states. Step 2, determine the flip-flop input and output equation. Step 3, derive the state equation of each flip-flop. 4, construct the next state and output tables. Step 5, combine these maps to form a complete state table. Step 6, draw a state diagram. And step 7, identify the circuit if possible. Here is our circuit. It consists of an OR gate, a D flip-flop, and the other gate. So the first step is identify and label the inputs, outputs, and internal states. The state is actually the output of a flip-flop. So we've got our AT here. Input is X and the output is Y. So state variable is stored in the flip-flop. The present state variable is AT, the output of the flip-flop. The next state variable, it is determined by the input to the flip-flop. And for a D flip-flop, it is the one. The input is X, output is Y. So what the next step is, we determine the flip-flop input equation, is also called the excitation equation and output equation. What input equation there? Output equation there. So what is D and what is Y as a function of X and the present state? D is this present state is fed into the OR gate with X. Output equation AT exclusive OR X. Now we derive the state equation of each flip-flop as a function of the developed input equation. It specifies the next state as a function of the present state and input. What will be the next state when we know D? For a D flip-flop, the next state will be what is at D. So what is at D is that is the function table of a D flip-flop. So the state equation will be AT plus 1, which is D is AT plus X. So we construct the next state and output tables. The state equation is that. Output equation is that. Why that? What type of machine is this? You see, the output is a direct function of input, so it's a milli machine. So your next state table with the present state, input, next state. Output table with present state, input, output. So you have all the combination of A and X, 0, 1, 0, 1, 0, 0, 0, 1, 1. Then you get the next state. So if this is 0, AT is 0, X is 0, the next state will be 0. That is where we find that. If AT is 0, X is 1, AT plus 1 is 1. Same thing to the output table. If A is AT is 0, X is 0, output is 0. AT is 0, X is 1, output is 1. So you fill in that. And the next state, you combine them into a state table. This is 0, 1, 0, 1, 0, 0, 1, 1. Those are still the same. Then you bring your next state here, your output there, you have combined. Remember, this table has different combinations. So after that, you can draw your state diagram. This is the state table we had. Present state is 0, input 0, next state is 0, output is 0. So that is your state diagram. Present state 0, input 0, then output 0, the next state 0. So you can easily draw that. Next step is identifying the circuit. It is not easy to do that from a state table, but it's easy to do that from a state diagram. How does this circuit behaves? It remains in state 0, copying the input to the output until a 1 arrives. The output becomes a 1, then goes to state 1, where it complements the input. That is how it's behaving, and it will never leave state 1. So this circuit is a two-state device with the memory represented by 1 bit. The circuit stays in state 0 from the start until a 1 is input, at which it goes to state 1 and remains there. So that's the verbal description of the circuit. It copies its input to the output until the first one is encountered in the input stream. After that, the output is a complement of the input. And if you check carefully, it's a serial 2's complement. That's basically the process of the analysis. Let's look at another example to cement our analysis. And note that we will skip some steps. So the first step is label your circuit. Where are your inputs? Where are your outputs? Where is your state or states? The state variables. The input is here is X. The output is Y. You've got two flip-flops, so you've got two state variables A and B. Now, the next step is you derive your output equation and the excitation variables dA, dB, inter and Y, which is out in terms of X and A and B. So you do that, get the equations. For those who did that, you will get those equations for A, T, B, and YT. I've just dropped the T to make it look better. Then from that, you can construct a table, an empty table with A, B, X, the next set A, B, and output Y. You have all the combinations 0, 1, 0, 1 of A, B, the present state and X, and for those, you now need to determine the next state and output from this equation. Let's look at this output. When A is 0, B is 0, X is 0, the output Y is 0. That is why that was gotten. Let's look at B here. When A is 0, A complement is 1, X is 0, B will be 0 there. Let's look at this A. A is 0. So that will be 0. X is 0, 0, so that will be 0. So you determine that. Remember, different books have different forms of the tables. This form and that are the same. In some cases, the most utilized one is this, but sometimes that could come in handy. So from that, on your own, draw the state diagram. You need to know which one is milli, which one is mho. Present state 0. X is 0, output is 0, the next state is 0, 0. That is what that means. So draw that diagram and finish on your own. That's the end of the first part of the lecture. We will continue with more examples in the second. Welcome to our second section of analysis of synchronous machines. We are going to continue from where we left. We had looked at analysis of a circuit with D flip-flops. We have actually used a table. So there is another way of analyzing is by use of what we call a characteristic equation. The function of a flip-flop can be derived from a table or an equation that relates the input to the next state of a flip-flop. That is what we call a characteristic equation. For a D large and a D flip-flop, the next state is what is at D. We can check here. For an SR large is given like that, and the other flip-flop is as shown. So we are looking at this analysis is of a D flip-flop, but we want to use a characteristic equation. The characteristic equation given is A. So we derive the excitation equation, which is D, which is X exclusive or Y exclusive or the present state. So that is what D is. Now the equation says the next state is what is at D. So the next state is what is at D, which is given by that. So that is our state equation. Once we have the state equation, we know we can get our table. We've got inputs X, Y, A. We fill in the right combinations, and then from the characteristic equation we can get the next state. Remember, here we don't have an output. So from here, 0 exclusive or 0 exclusive or 0, you get that 0. 0 exclusive or 0 exclusive or 1, you get 1. So you do that fill, and then you get your table. And then the diagram is just from the table you can construct your diagram. That is basically straightforward. Now let's look at the next. It's very easy when you're dealing with the D flip-flop. Let's look at the next, which is a JK flip-flop, and it will summarize most of what we've been saying. Analysis is straightforward. The next state values of a sequential circuit can be derived from two things: the characteristic table or the characteristic equation. So let's look at the first procedure using the characteristic table. You determine the flip-flop input equations in terms of the present state and input variables, list the binary values for each equation, and use the table to find the next state. The table will give you the next state from the present state for the inputs, the excitation equation. So let's look at that. Here is your circuit. We say the first thing is you analyze, you label the circuit. That is your X, that is your A, that is B. These are your state variables, A, B. There is no output here. The next, you get your equations, in flip-flop input equations. Whichever method, you must get them. So you have to get JA, KA, JB, KB in terms of X, A, and B. So you do them on your own. You will find they are given by JA is B, KA is B X complement, JB is X complement, KB is A exclusive or X. So now, be careful. The first step, we labeled the circuit and derive the flip-flop input equations, these ones. And then the next is you create a blank state table, step 3. With all the different combinations of A, B, and X, 0, 1, 0, 1, 0, 0, you know that. And then step 4, you fill in from these equations, for these characteristics, you fill in the input equations at the flip-flop. That is step 4. If A is 0, B is 0, X is 0, what is JA, JB, KA, KB, JA, KA, JB, KB? JA is B, so JA, that column should be the same as that. JB is X complement, so the JB complement should be the complement of that. So you fill in those from that. Now, to get the next step, remember we don't have an output. Let's look at the first flip-flop A. If the present state is 0, JA has 0, KA has 0. What will be the next state of A? We go to the table. That is why we say go to the table. JK is 0, 0. There will be no change. So if the present state is 0, there should be 0 there. That is what we are saying. Present state, flip-flop inputs are 0. You look there, no change. So A should be what? No change. For B, if the present state is 0, JB, KB will be 1, 0. What do you expect there? 1, 0 means it is set. So that is why that is set. So now we'll go, let's look at another example. keep on repeating. Let's look at that. The present state is 0. The flip-flop inputs are 1, 1. We go to the table. 1, 1 means complicate, so complement, so we get a 1. So you fill in that, and there you have your present state input and next state. You have your table. Procedure B. Same JK, but now using the characteristic equation. That will be given. The characteristic equation for A is J, A complement plus K complement A. For B is J, B complement plus K, B complement B. These are the input equation derived as before. So you just substitute this input equation in the characteristic equation and simplify. You find the equation, the next state equation for AT should be given by that. BT should be given by that. Now with the next state, fill in the combination of present state and input. Then from the equation you get the next state. After that you can draw your state diagram. So it's simple. People don't like it because of the simplification here and the failure of substituting things there. Otherwise it's basically simple. So the analysis of flip-flops is always the same. You can use the table or the characteristic equation. Let's look at another example of a T flip-flop. What do? This is your circuit. You label your input is X, your output is Y, your excitation variable, your flip-flop variables is A and B. This is the table, this is the characteristic equation. You can use whichever. So you get your input equations TA and TB, and your output equation Y, which is just AB. So you determine that Y is AB, TB is that. We will use both methods. So you label your circuit. We did that. Create a blank table. This is your blank table there, and then you get your TA, TB and Y there, and then you fill in the different combinations there, and then you do the same thing. You have the flip-flop inputs. If the present state is 0, TA is 0. When it is 0, there is no change, so A will remain 0. Fill in the whole of that. Let's look here. Present state of B here is 1. TB is 1. When it is 1, it toggles, so B will be what? 0. Why? You get it from that, so you fill in that table. Then from here up to there is your state table. Don't redraw it again, you'll be wasting your time. That is using the table which most people prefer. Characteristic equation. The characteristic equation for a T flip-flop is given by that. You've got TATB, that there. Substitute into your equations. You get A is that. And B is the next B equation is given by that. Then from this equation, you fill in these combinations. Then you can derive the next state and Y, and then you can draw your state diagram. Note that from this you can know that it's a Moore machine. So that, and then you can describe the circuit. And when the input is 1, the circuit behaves like a counter. When the input is 0, it stays in its state. So that's the description. So in conclusion, the analysis, you start with the circuit diagram, you label your inputs, variables, state variables, outputs. You derive your flip-flop input equation and the output equation. Then the next is to develop the state diagram and state table. But there are optimization methods of minimizing that we look at, and then you can describe the circuit. So the procedure never changes. So that is what we have done. Attempt the tutorial is the next one that we will look at before we go to decide. Thank you very much.